Hi everyone, welcome to the first episode of The Broke Engineer, hosted by yours truly, Harshit Sarvanan. You guys might be wondering why I'm starting this all of a sudden, and the answer is pretty simple. It's for the college apps. Okay, no, but seriously though, it's because when I first started at FRC, I was extremely clueless on everything going on. FRC, for those of you who don't know, by the way, is First Robotics Competition. Teams go out, compete in different events. And my experience was that I sort of just thought that just going there for a year would just automatically give me the experience I needed. But, that's not exactly how it works. I mean, you may learn a thing or two here and there, but you gotta take your own steps. You have to watch your own YouTube videos. You gotta ask your own friends for help. And you gotta get into the process through experience. But the problem with a lot of channels is that I haven't seen people go through the full process, the design, the CAD, all of that. And I wanted to give you guys a new perspective on engineering. And I just wanted to kind of create a community where we could all help each other and introduce ourselves into engineering. So, yeah, I hope you guys enjoyed today's video. The first thing I wanted to create for this channel is a sort of personal helper. No, not you. You. It's the mechanical robotic arm that you see in the Iron Man movies and in industries worldwide. They're usually used in packaging, but I'm going to be using it for irresponsible reasons. But yeah, it's going to be a fun build. As any good engineer would, I started off with a 2D sketch of the robotic arm. So this drawing has 3 degrees of freedom. One in the bottom, being able to turn it 360 degrees this way, and 2 joints here and here, allowing it to move left and right. And there are a lot of ways that you could accomplish this, but the first couple I thought of were these. So in terms of the base down here, the 2 ideas that I thought of were using an interference fit and using a turntable bearing. What an interference fit is practically jamming one piece into another. So assume you had this puzzle block looking piece over here and something to fill the gap. The problem is that this one is slightly larger than this piece, right? So, but if you shove them in strong enough, it kind of holds it into place really tight. And using the same idea, you could construct a base piece over here, which has a smaller gap. But shoving it in would kind of lock it into place so that as the motor spins one direction, the entire robot also spins in that direction. The other idea was using a turntable bearing, and the concept of this is kind of like the concept of gears. So in gears, while using gears, say like this, pretend that's a gear. If the gear rotates left, for example, it spins the gear that's next to it right. Using this same idea, kind of, if you use a compliance wheel over here, as this wheel turns one direction, it kind of rubs off on the bearing, which can rotate freely, spinning it the opposite direction, or in this case, right. So if the robot was to be attached to the outer part of the bearing, it would be able to rotate the entire robot 360 degrees. At the end, I ended up choosing the turntable bearing because it could just hold up for a lot longer than interference fit could. The problem with an interference fit is that if you had enough force to push it into place in the first place, the entire weight of the robotic arm might be able to push this base over here down here, causing problems. And even if you were to solidify the base with an indestructible material, the weight of it would still wear down the sides of it, creating other problems. So in the end, we ended up choosing the turntable. I ended up choosing the turntable bearing because it just wouldn't wear out as soon. For the joints, that's a pretty simple idea. We're going to have two wall-like bases on the sides, bearings on the sides as well to hold in the shaft over here. And in addition to holding the shaft, it also allows it to spin freely. Through the shaft, there's going to be the arm and shaft collars to hold it in place. The arm is also going to need to be interference fitted in really tightly with maybe glue on the sides to really hold it in place. But yeah, that's the idea or design behind the robot. The next challenge was choosing the right motor. So the three main motors that I looked at were normal DC motors, stepper motors, and servos. In terms of normal motors, I chose Sims, and in terms of the stepper motor, I chose a NEMA 17. So normal motors, they are less accurate, but the advantage of using them, or specifically using a Sim, is that something called a versaplanetary gearbox can fit in with this Sim perfectly. And what this versaplanetary gearbox does is that it increases the torque of the motor. And in addition to that, you can add attachments like a hex output shaft or a sensor. And why this would be useful is because wheels like the compliance wheel over here only have hex outputs. So converting from a normal motor's circular output to a hex output with like other connectors could be more of a hassle. So using Sim motors would just make the job easier. Next up is stepper motors. They're really strong at a standstill. They have high torque. Torque, by the way, is like the rotational force of something. They rotate in steps, kind of like a clock would. And that makes it easier for people to calculate how far it's going, what it's doing, where it's at. And also, it's really small. Servos, they have similar advantages. The problem is that they're meant more for speed than stepper motors are. And in case of this robotic arm, we're not really going for speed. We want to be slow and steady, but also strong enough to lift the entire arm. Also, the ones I found online were kind of expensive as well. So what did I end up choosing? I chose the Sim motor for the turntable bearing, or more specifically, the compliance wheel that spins it. And I chose a stepper motor for the arm joints. So yeah. And finally, the last thing we need to go over is sensors. So the only sensor that I see that we need here are rotary encoders. And what these do is to help determine the position of the motor shaft so that whoever is coding can tell where the robot is constantly so that you can automate, random features onto it. With the sketches and design completed, I moved on and finished the CAD as well. Unfortunately, you guys won't be able to see any more of my beautiful artworks anymore. But Yeah, I'll go ahead and show you guys the CAD. Okay, so here in front of us is the 3D CAD that I modeled. It has the turntable bearing that I mentioned before with the compliance wheel to spin it, one joint over here and one joint over here. So I'll explain this from the bottom up. So down here we have the base with a cap that you can screw on. In this gap, that's where the batteries and Arduino, which controls the robot, are going to go. And the holes above are so that the wires from the battery and Arduino and all that can connect to the motors up here. This cap over here provides space for the sim motor, which is down here with the versaplanetary gearboxes to increase the power. This spins this hex shaft axle, which turns the compliance wheel, and as the compliance wheel turns, it turns the turntable bearing along with it, as you can see here. Next up is the joint. So this motor is connected to the axle, and as the axle turns, it turns the arm along with it. And then the same thing for this one over here. As you turn the axle with the motor, it turns the arm as well. How this works is that there's going to be some bearings placed on the 3D prints over here, and that bearing can hold the axle in place as well as allow it to turn smoothly. Then we have the shaft collars over here, which hold the arm in place. And just in this small section, you're going to see a lot of interference fitting, just because that's an easy way to get everything to fit properly. So if you see this bearing over here, you'll see some red overlap onto the bearing, and that's because the gap from the 3D print is actually smaller than the size of the bearing. So it's going to require some force to kind of push it in there, but once it's in, it's hopefully going to stick for pretty long. I did the same thing with the arm. The hole in the arm is slightly smaller than the axle, so it's going to also require it to be pushed in. But it still might not lock in, so it might need some Gorilla Glue on the insides to make sure it sticks. Finally, there's two more. So there's some shaft collars over here. They tighten on and hold it into place. And the last two are back here. So if I had this motor, you can see this yellow piece over here. You'll see some color overlap, and that's because this yellow piece is bigger than the hole for the axle. So it's interference fitted onto it, so it sticks inside. And then this hole is also smaller than the size of the NEMA 17 output, which just makes everything stick on together well, so that as the motor turns, it's connected to this and turns along with it. And then, of course, I had to use my advanced computer science keyboard to Control-C, Control-V this onto this, since it works the same way. With the CAD done, it's time to move on to gear ratio calculations. Trying to figure out what's the right strength that the motors need to be able to actually rotate the parts of the robot. But before I go ahead and start, I'd like to apologize for not making like a speed run of my CAD. I sort of forgot to. Okay, so now I'm going to go over gear ratio calculations. But before I begin, I want to go over what gear ratios are, what's the point of them, how do they work, and all of that stuff. So to begin, you guys have probably seen a notation like 3-to-1 gear ratio or 3 mechanical advantage, and they essentially mean the same thing. It's output to input or driven to driving. And what that means, I'll explain through this image over here. So assume that a motor is directly powering this 10-tooth gear, right? And as the gear spins left, the right gear with 30 teeth spins right. What this does, well, first it makes the 10-tooth gear the driving gear, and the 30-tooth one the driven one, creating a 3-to-1 gear ratio by doing 30 teeth divided by 10 teeth equals 3. And what this does is assume that the motor provided a torque of 10 Nm. The 3 multiplication would end up giving an output of 30 Nm. But why is this calculation so important? It's because as you multiply and increase the torque of the motor from 10 to 30, you're also decreasing the speed of it by 3 times. So if the speed was like 100 RPM, oh no, that's too hard, 30 RPM, then it would end up as 10 RPM. And that's why it's so important to find the right balance between the perfect gear ratio so that you're able to keep a high speed while also being able to turn the robot in the direction that you want with the right strength. And of course, one of the major components of this is torque. And it's something that we need to calculate. So first, what is torque? Torque is defined as the twisting force that causes a rotation. Essentially, how much the motor has to provide like rotational power to be able to rotate a heavy load, right? And it's usually defined as force times distance. And since it could be placed, the arm could be placed at any angle, it's usually combined with some trig equation, sine or cosine. In this case, sine theta. Now we're calculating for the holding torque, or the maximum amount of torque to hold the arm in a standstill. Maybe like this. So since we're calculating for the maximum torque, we're just going to set the sine theta to 1, since that's the maximum that sine can be. So we're just going to say this is equal to force times distance. So to calculate for that, we're going to need some information, specifically the weights of everything, which I put over here, and then the measurements of everything, which I put over here. And typically, you get the torque in OZ inches or NM as the measurements, but NM is probably the more common one. So to calculate in NM, we're going to need to use kg and the metric system meters. Okay, so first we need to find the weight of the arm that the motor is holding from here, and the weight of the arm that the motor is holding from this point. Alright, so for the 1.09 meters, that contains one motor, some gearboxes, 2 arms, 2 joint holders, and some extra weight from bearings, shaft collars, etc. So that should equal approximately 2.891 kg. Next, from this point over here, there should be, one arm, 2 joint holders, and the extra weight, the bearings, and that should equal approximately 1.304 kg. And now to calculate for torque, force times distance, I'm going to say torque of motor number 1. I'm just going to label this as 1 and this is 2. That's going to be the weight, which is 2.891 kg, times the gravitational constant in meters, which is 9.8 meters per second squared, times the distance, which is 1.09 meters. And this should equal around 30.88 nm. Or actually, sorry. The gravity is spread across the entire arm, so the weight should be at the halfway point. So it's actually going to be 1.09 meters divided by 2, turning this 30.88 into 15.44 nm. Next, we're going to calculate the torque from motor number 2, which is going to be 1.304 kg times the gravitational constant times the distance, which is 0.47 divided by 2, which, let me calculate that real quick. Is 3.005 nm. Then, in addition to this, motors often lose some of the torque that they output due to various reasons. So, I think a good safety factor that you want to put on it is 0.7, which is practically like saying that you're only going to get 70% of the expected output. So, to calculate that, we're just going to divide both of these by 0.7, getting 15.44 divided by 0.7, 22.06 nm, and then 3.005 divided by 0.7, 4.29 nm. So that's the torques for the two motors, the NEMA 17 stepper motors, to carry the weight of the arm. So, of course, we're going to need more than this to be able to actually rotate the arm. Next, we need to find out the amount of torque to spin the bearing that's holding the entire robot. And that's done a little bit differently. So here we have a representation of the drawing of the robot, and we're going to pretend that the arm is a cylinder in this case, just because it makes the math easier. So if it was a cylinder, the radius would be 0.025 meters, the weight would be 4.536 kg, and the height would be 1.09 meters. To calculate the torque in this case, it's going to be equal to the the moment of inertia times angular acceleration. And what the moment of inertia is essentially how much an object resists angular acceleration. And the way that you calculate for the inertia, or the moment of inertia, is different based off of what shape you're using. So since we're using the cylinder, we're going to go with these two equations. They're different based off of the orientation of the cylinder, but since we don't know which one requires the most torque, we're going to calculate for if it was parallel to the axis or if it was perpendicular. So if we calculate for these two, we should get 1.8 here, and then 2.7 here, using mass, height, radius, and length. Since 2.7 is the greater of the two, we're just going to continue with the calculations using this number. Next, we need to calculate for the angular acceleration. And the equation for that is equal to the rate of change in radians per second, final minus the initial divided by time. And how we're going to do that is by using this chart over here. So W represents the RPM starting out, and then WP represents the RPM as it ends, and let's say in 1 second. So it needs to go from 0 RPM to 15 RPM in a second, which is like 1/4 of a revolution per second. So to calculate for this, we're going to need to do 15 RPM multiplied by a revolution, which is 2 pi, and then multiply this by 1 minute over 60 seconds, converting it to radians per second, right? So 1 over 60. And this totals out to pi over 2. So now that we have the angular acceleration, we can just put these two together to get the torque is equal to 1.35 pi. And if we divide this by our safety factor, or by adding a safety factor, and dividing by 0.7, we get around 6.06 Nm. So yeah, that's the torque required to spin the base. Now that we've solved for that, we need to calculate the right gear ratio that we need so that it's able to spin efficiently with the maximum amount of speed, right? So we have the values over here, the 22.06 Nm from the motor number 1 stepper motor, 4.29 from motor number 2, and then 6.06 for the sim motor that's rotating the base of the robot. So to calculate this, it's pretty simple. It's just taking that torque required, 22.06, dividing it by the torque output of the stepper motor here, so 0.45, getting approximately 49.02. And then you have to add a safety factor on top of that as well. So this is what an actual safety factor is. I've been saying 0.7 by accident. But a safety factor is where you have to add an additional value on just for safety. So we're going to say more than 50, or the closest we can get to that number, which I think might be 60 with a this gearbox that I can think of. But whatever it is, it has to be more than 50. Next is the 4.29. So 4.29 divided by 0.45 is 9.533. And with an additional safety factor, we're going to say more than 10. So I think 15 is a good number for mechanical advantage. Next for the sim motor, The sim motor provides 343.4 OZ inches of torque, which is approximately equal to 2.42 Nm. So we're going to say 6.06 divided by 2.42. And that's not really worth calculating. It's around 3, but we're going to go with the safety factor and say 5 mechanical advantage. So that's how you calculate the mechanical advantage or the gear ratios that you need to make your motors work. There's different ways that you can use gears in this case. The two main ways are using planetary gears, which is really common in FRC, or just directly using 2 gears, like the example I mentioned before. Versaplanetary gears are objectively the better ones because they're really compact. They're like one small box, and it could, with just 3 of them, you could go up to like past 100. Because as you stack them on, you just continuously multiply the mechanical advantage over and over. So say the first one was times 3, the next one was times 10, the next one's times 10. You'll have a total output of times 300, right? So versaplanetaries are objectively one of the best gear reduction gearboxes, but they only apply to a select few motors, so we're going to need to find some alternatives for the NEMA 17s. However, they do work for the sim motor, so we could use versaplanetaries for this one. So I created a replica of the robot kind of in Inventor. This is the base. It has the same measurements. And this piece over here is supposed to represent the arm. It has the same mass. And this is just such a stress test to see if it's able to handle all the weight. So let's go to environments, stress analysis, and simulate. Okay. So as you can see, it kind of gets squished a little bit, but it's mostly okay except for the bottom part, which might take a little bit too much stress, but it should probably be able to handle the robot. If you guys enjoyed today's video, please consider liking and subscribing. And if you don't feel like it, but yeah, hope you guys enjoyed today's video. I would appreciate it if in the comments you guys gave me suggestions for the next couple of videos or any way to improve my design. But yeah, I'm really excited to see where this is gonna go. And thank you for watching.